So today's lecture is actually going to be a joint lecture between me and Nicholas. So we will be talking about particle physics and kind of delving into what that is. So just a brief overview of what we're going to be going into, but we should just get right into it. So what is a fundamental particle? Well, so dictionary definition, a fundamental particle is one that cannot be broken apart into smaller parts. And I think this idea kind of developed long ago in kind of 460 BC when we had the Greek philosopher Democritus kind of developed the idea of the atom. And he kind of posed the question, like, what if you took like any kind of piece of matter and just broke it in half and kept on breaking it in half until you could no longer break it up. And like whatever you were left with, that's what he called an atom. However, in reality, it's not really possible to ever really know when you've kind of reached reached kind of the smallest fundamental particle. And you can kind of see that throughout the history of the model of the atom, where we've kind of developed from just this like building block idea to like there was like a plum pudding model with like smaller electric charges on it. And then now we kind of know, okay, there's actually a nucleus at the center with a proton and a neutron. And kind of see how like we've been continually kind of developing our idea. And so it's kind of fair to probably say that it's not possible to ever really know. And in fact, as we've kind of gone deeper and deeper, we've kind of reached these difficulties. And I guess just as a quick kind of starting question, can anybody think of what these difficulties could be? Like, why are we kind of hitting this roadblock of like not knowing whether this is truly the fundamental particle we're talking about? Does anybody have any ideas?
Yeah, broadly the question is how like just think about like how would you be able to tell if a particle was fundamental or not? So yes, our own physical limits, that's true. But what exactly do you mean? But yes, that's the basic idea, kind of.
Yeah.
Okay, yeah, we can't measure it or see it at that level. I think that's pretty close. Or
Yeah.
That's like, that's
I mean, that's pretty much what it is like at some point, like the way we even, I guess, like perceive what there is, like that would just break down. And also like when you kind of look at the experiments that are being done in particle physics, you can kind of see these really elaborate and like really expensive machines that are built, and they require a lot of energy. And so in kind of particle physics, we like to maybe more than emphasizing what really is a fundamental particle, maybe see broadly just kind of the scale, the energy scale in particle physics. So we kind of recognize that at larger energies, we have a higher mass, which also kind of broadly is equivalent to smaller lengths and shorter times. So we can kind of see that in kind of a description of a wave where you know that electromagnetic waves that have a higher frequency have a higher energy. And this also comes from, like if you think of just like how a wave is drawn, you can say, okay, well, if it has higher frequency, then it has a shorter time and a shorter wavelength. And you can also see that in the de Broglie wavelength equation, where you see that a faster particle has a shorter de Broglie wavelength. And so we kind of broadly associated smaller particles with higher energies. This might seem kind of unintuitive at first because you're like, wait, didn't we just kind of say that higher masses have larger energies? So why are we associating like small particles like electrons with higher energies? But the reality is we're not, when we say higher energies, we're not describing the rest mass energy, but we're actually describing the energies of the interactions between those particles. And we'll kind of delve deeper into that concept later. But as just, I guess, particle physics as a subfield is also kind of called HEP, or higher energy physics. So broadly, you can say that we associate those smaller particles with higher energies. And that's, in fact, why when we're doing these particle physics experiments, we need these really large, really high energy accelerators, like I mentioned before. And so some of you might know kind of this big experiment going on called CERN, which has the LHC, which is a Large Hadron Collider, and it is actually the biggest machine in the world, like the biggest man-made machine in the world, which is pretty cool. And it's like, let's see, it's 27 kilometers in circumference, and it's 175 meters below, like underground. So it's like this really big machine that's like billions of dollars, and we just like put in a lot of money to like accelerate super small particles at really high energies to kind of then investigate particle physics. So keep this kind of relationship in mind as we kind of continue on with the lecture.
One example that sort of makes the point pretty clear is, suppose you have, so like the example I like is, let's say you had like a table and you wanted to ask whether the table was a fundamental particle. Of course, the only way to actually know if it's a fundamental particle is if you can break the table. But if I like use these low energies, like I use my hand to try and break the table, I'm not going to break it. And so I'm going to think it's fundamental. But the fact is that if I had the ability to like increase the energy that I probe the table at, then I will break the table, and then I will realize it's not fundamental. And if I increase the energy even more, I could start breaking, you know, the molecules that make up the table, or the atoms, or the particles that make up the atoms, and so on. And so that's the sense in which increasing your energy sort of allows you to probe smaller.
Yeah. Next slide.
Okay. Yeah, so going a little bit deeper, I sort of wanted to talk about some of the shortcomings of quantum mechanics, as we told you about before. And the shortcomings very much come to the forefront in particle physics. What do I mean by this? Well, so just as a reflection, classical physics broke down at the de Broglie wavelength, which is basically h/mv, which is the basically the wavelength of anything. So like an electron that's moving might have a de Broglie wavelength, and so on. And so in that paradigm, when we talk about quantum mechanics, like, you know, classical mechanics isn't true, but it's sort of true as a limiting case of quantum mechanics. However, quantum mechanics is fundamentally non-relativistic, right? So all of that stuff we told you about in special relativity, especially general relativity, but even special relativity is not taken into account at all in quantum mechanics. Even though the particles are sort of very small, like electrons, they're very light, they're moving fast by our standards, they're still moving significantly slower than the speed of light in any problem that you could tackle with, you know, the standard Schrodinger equation. However, if you think about it, this is not sort of a very good way to, this is sort of not a super complete, you know, description of reality. And this becomes very evident in particle accelerators, where your particles actually are traveling basically at the speed of light. And so you do have to take into account both quantum mechanics because they're small, and relativity because they're fast. And so the question is, how can we actually reconcile those two concepts together? Yeah.
Next slide.
Yeah. And so just as a reminder, in quantum mechanics, we basically govern evolution of our wave function with something called the Schrodinger equation, which is written here. It looks kind of complicated, but just as a reminder, it basically is the same thing as the conservation of energy. It just says kinetic energy plus potential energy is equal to the total energy. So one thing that people don't talk about particularly much is that Schrodinger actually already knew about SR, special relativity, and he originally wrote down a sort of more quote-unquote correct relativistic version before abandoning it. I'll tell you about that in a moment. And then he went back and he wrote this simpler equation instead, and that has been basically the paradigm. As long as we're way below what's called a Compton wavelength, which is h/mc, this is fine. So notice that the Compton wavelength looks very similar to the de Broglie wavelength, but we've replaced v by c, and that should make a bit of sense. That's sort of like, as a hand wavy thing, it's like the quote-unquote wavelength of a particle that's traveling at the speed of light, kind of, like that's what it looks like. Of course, like that's not really a super meaningful concept. But more precisely, the Compton wavelength corresponds to an energy equal to the rest mass of the particle. So like the length corresponds to an energy of mc squared, which is like sort of the energy stored inside the particle just because it exists. Next slide. Yeah, so as I said, the Compton wavelength is basically this length scale corresponding to the rest mass energy. which is kind of important if you think about it, because in non-relativistic quantum mechanics, you can't really, there's not a very like good way of implementing like particles being created or destroyed. Like maybe there's some way that you could like hand wavily, implement this, but fundamentally, like there's no like uh like uh, like ground up
I love
way.
going pedally, right? It makes it
Oh,
really hard to go
is
to
there
classes when
is
you're
there
so
somebody
cute
that
and you want
should be muted?
and I just
Thanks.
Okay.
So in non-relativistic quantum mechanics, there's not really like a natural framework for particles to be created or destroyed. But if you're probing below the Compton wavelength, then your length scale corresponds to energies which are about mc squared. So like particles can like the fluctuations in energy are such that the particles can just be created or destroyed all the time. And so at length scales below this, the particle number isn't very well defined, and you just sort of get particles popping in and out of existence a whole lot. Next slide. And so actually Schrodinger wrote down an equation based off of this like E equals mc squared like equation, including the momentum, as we talked about in special relativity, but he abandoned it. But while he abandoned it, scientists Klein and Gordon later actually recovered and wrote down the equation again and published it. And it looks like this bottom expression, which again looks kind of cryptic, but what it actually means is something very similar to the top. It just says like the first term is basically like it contains the E squared and the P squared part, and then the other one is M squared. And so why did Schrodinger actually throw this equation away at first? So we can move on. Here are some problems with the Klein-Gordon equation. The Klein-Gordon equation allows particles to have like the following energies, so the ones on the right. So in particular, energies either greater than mc squared or less than negative mc squared. And so you can see that the Klein-Gordon equation sort of, the positive energies make sense because if you think about it, like an electron can't have less energy than its rest mass, which is when it's not moving. But it also seems to have an infinite ladder of negative energies below minus mc squared, which seems very odd because it's not so much that the energies are negative. That in and of itself could be like maybe okay. But the problem is that there's an infinite ladder of negative energies. Like it allows like basically infinitely negative energies. And as you remember in thermodynamics, particles don't like to be at like given a very long time, the energy sort of dissipates away and the particle sort of goes to the lowest energy that it can. And so if you think about it, this means that like if this were true, then the entire universe would be basically unstable and particles would just sort of fall in energy forever. And we know that we're like alive in some sense of the word nowadays, but that sort of proves to us that this is not a very physical description of what's happening. Next. There's another problem which is very glaring, which is that the Schrodinger equation predicts that or the Schrodinger equation, or like what you want out of a quantum mechanical equation is that it describes like the probability that you find a particle somewhere. But the Klein-Gordon equations actually has a very big issue, which is it predicts the probabilities are allowed to be negative, which doesn't make any sense, of course, because you want the probability to be positive everywhere and add up to 1, because that's just how probability works. But nevertheless, despite all of that, the Klein-Gordon equation still has its uses in describing spinless particles, so particles without like spin, as the name suggests, and with some reinterpretation of probability to mean something like charge, which is allowed to be negative, it has its uses. But ultimately, it's sort of a little bit problematic in the way that it's interpreted. And so if we go ahead, so Dirac's insight was to basically notice that the negative energies coming from the Klein-Gordon equation was because the Klein-Gordon equation is what's called a second order differential equation. You don't have to know what that means, but basic idea is that when you solve it, you basically are like, if you think about it, solving like a quadratic equation, and quadratic equations have two roots, like a positive or like a larger and a smaller root. And this is sort of fundamentally a similar concept to why the Klein-Gordon equation has negative energies. So he's like, well, let's not write down this quadratic equation. Let's write down a different equation, like the Schrodinger equation doesn't have this problem because it's first order. So why don't we try and write a relativistic equation like that, which is first order, but which sort of matches the Klein-Gordon equation in some sense. So that's what he did. And if we move on, so this leads to the Dirac equation, which is written over here, which is it's sort of like the square root of the Klein-Gordon equation in some sense, but it's actually a little bit more subtle than that. So so Dirac actually realized, he went through the math and he realized that this object psi, which is the wave function, really only can like make sense in this context if the wave function had like 4 parts to it. Like, so this is like 4 wave functions kind of. It's not like a single one like in Klein-Gordon or in Schrodinger. And that's sort of interesting. Like he literally, you know, went through the math. He's like, it couldn't be 1 or it couldn't be an odd number. And then he found out it couldn't be 2. And then the sort of the lowest number of components it had was 4. And so, so if we go to the next slide, so what does the Dirac equation do for us? Well, first of all, it solves the issue of negative probabilities. It turns out you can work it out and this issue goes away. However, it turns out to still have an infinite ladder of negative energies, which is also like not desirable. Like that sounds like the issue you were trying to fix, but because of like you didn't exactly turn it into like a single component equation, you still have this big issue about negative energies. But there are some things that you win on, which is that the 4 components, like the 4 parts of the wave function that I talked about before, actually split up into 2 pairs of 2. So like, and like each of those pairs behaves as like spin up and spin down. And so Dirac had basically discovered where spin had come from. And so people like Wolfgang Pauli previously had written things down like the Pauli equation, which basically, you know, they knew about spin back then, but they didn't know where it came from. And Pauli had sort of an intuition that spin was a fundamentally relativistic concept. Like, it's super weird. Where did this come from? But Dirac actually, Dirac's insight was that he was able to actually derive where spin came from. Like the behavior of the equation itself sort of implemented spin just sort of naturally. And of course, that's good. And so we still have this issue of like, how do we make sense of these infinite, like this infinite ladder of negative energies? So we turn to the Dirac sea. If we go to the next slide. Dirac knew that electrons are fermions and could not occupy the same state. And so he wondered if there is an infinite sea of negative energy electrons. So I said that you're allowed to have electrons which have energy above mc squared and below minus mc squared. That should be minus mc squared on the bottom. But he said, what if every possible electronic state below like 0 or below minus mc squared was already filled up? Because if it was already filled up, then any electrons that, like any additional electrons would just float on top. And of course, you'd think that they'd like to decay, but they can't because there are already electrons down there and they can't occupy the same state as another electron. And so that's very fine and dandy. And that's very nice to wonder about. But of course, there are actually predictable consequences to musing about this concept, which is called the Dirac sea. So for example, it predicts positively charged holes in the sense that, like, let's say that you had this sea of electrons and you're just missing one, then that means that there is basically a hole where there's an electron should be. And so that sort of looks like a positively charged hole that's moving around. That looks like it has like the same mass as an electron. In addition, you might imagine that because there's just electrons everywhere, you could imagine shining some laser, like inserting a ton of energy, and in fact, an energy equal to the sort of the transition gap mc squared, 2mc squared, and you would be able to excite an electron out of the Dirac sea. The electron would float on top, and then the hole would also move around. So you'd have like an electron and also a positively charged hole that looks like an electron. And also, you might have the possibility of, like, if an electron comes near a hole, it might fall into the hole and then release an 2mc squared amount worth of energy. And so, like, you know, this sounds super crazy, but actually Dirac was like, maybe this is actually how the world works. And like, maybe in fact, if you had this much energy, you could actually get particles which have opposite charge and behave exactly the same and annihilate when they reach their normal counterparts. And this is actually called antimatter. Dirac actually predicted antimatter before it was actually observed. And that was like sort of an insane insight. And so this is the other degree of freedom. So I told you there are 4 components, and so they split up into 2 pairs, which were spin, and then each of those pairs, like one was matter, one was antimatter. And like I said, it sounds super crazy, but actually people went and they checked, and that actually exists. So if we move on to the next slide. But nevertheless, this fact that there are some like sort of problematic ideas with the Dirac sea, which are just not very aesthetic, which are like, for example, the Dirac sea predicts there's an infinite sea of negative charge like everywhere in the universe, which seems kind of insane. And also it treats matter and antimatter on a different footing. Like if you think about it, like what's to say that like matter isn't the holes and antimatter is the actual particle, for example. And so fundamentally, we need an even newer theory in order to actually, properly tackle relativistic quantum mechanics. And so when we went from classical to quantum mechanics, that's called quantization. And so when we go from quantum mechanics to an underlying theory, that's called second quantization, because we're very unimaginative. So if we move to the next slide. So just as an analogy for how this procedure works, in classical mechanics, we had equations which describe like a particle's like position and momentum, or which basically describe the state. So like position and momentum are like variables which evolve over time and determine like what state the system is in. In first quantization, we think of position and momentum as operators on wave functions, which now describe the state. So like x and p aren't really like the things describing the system anymore. It's really the wave functions which describe, which like encode the information about what the system looks like at some time. And that's like standard quantum mechanics we told you about in the last 2 lectures. And in second quantization, so now the wave functions themselves are like operators on underlying space. And that underlying space now describes the state. Describes the state, not the space. And so we have to sort of remember exactly how this works. So in quantum mechanics, recall that like we talked about the Schrodinger equation and how it's like the conservation of energy and stuff and something like that. And like the basic idea is that, well, the classical mechanical equations aren't exactly true, but what is true is that in some limit, the quantum mechanical equations have to revert back to the classical equations. While it's also similarly true that these sort of the Klein-Gordon and Dirac equations are like not totally true in like an exact sense, they're true as like constraints on like the deeper theory. Yeah. So if we move on, so quantum field theories, which is sort of what's the result of second quantization, are theories which describe particles as excitations in quantum fields. So the classical example is like photons are excitations in the electromagnetic field. So you can sort of think about this as being like there's a harmonic oscillator everywhere in space. So people like to joke that physicists like are in love with harmonic oscillators and make everything into harmonic oscillators. So what's a more beautiful theory than putting a harmonic oscillator everywhere in space? I'm sure. I think that the statement that it's an elegant theory is not exactly uncontroversial, but nevertheless, like when we talk about photons being excitations in the E&M field, that's pretty plausible given what we told you about before. But a sort of a more out there example, which is actually turns out to be true, is that electrons and positrons, or positrons are anti-electrons or antimatter electrons, these are both excitations in the electron field. So in particular, there's an electron field which permeates all of space, and the wiggling in that field, like wiggles in that field, are interpreted as electrons or positrons. And indeed, any particle that you can think of is really just some underlying field that's wiggling around in some way. And so in this formalism, you can see how like creation and destruction of particles is not such a big deal because, like instead of being like, well, like this, the idea of particle like oscillations arising and going away is a little bit more natural in this formalism. Yeah, so next slide.
Kind of thinking of it as like constructive, deconstructive interference, just like waves, basically. But
Yeah, they're basically like harmonic oscillators, and yeah, where the like, remember that the level of the harmonic oscillators are like evenly spaced, if you remember that. And so like each of those levels represents a different number of particles. Yeah, so and okay, I'm getting a little bit ahead of myself, but quantum field theories often have a very big problem, which is that if you have an infinite number of quantum harmonic oscillators everywhere, well, I don't know if you remember this, but the lowest energy in a quantum harmonic oscillator doesn't have 0 energy. It has like a little bit more than that. And because you have an infinite number of them sort of crammed in everywhere, this predicts like an infinite energy density. Not just an infinite energy, but an infinite energy density. So like everywhere has an infinite amount of energy. And that sounds like it sucks a lot. So you might like try and say like, oh, well, this theory doesn't work up until like some point where it breaks down, like the Planck length or something. And this would give some prediction for exactly how much energy there is. So you might say, well, I've heard about this concept of like energy, just being in empty space, and maybe like and like maybe that's like dark energy, like maybe that's the same thing. But it turns out if you compute it and you compare it to the actual measured value of the cosmological constant, this turns out to be 120 orders of magnitude different. So that's not 120 times, that's 120 orders of magnitude. So that's like 1 with 120 zeros after it. That's like the difference between like the prediction and the reality. And so this may be one of the biggest, most disappointing, incredible disagreements and or embarrassments in history of physics. And so far, this is an open question, and you would win a Nobel Prize if you could figure this out and prove it. Yeah.
Final paper topic. No, just joking.
Yeah. It's extra credit.
Yeah. You get an A.
And so QFT gives some other unintuitive results, like the spin statistics theorem, which sort of put to rest what exactly is a fermion, what is a boson. It turns out that particles with a, quote, half integer spin are fermions, whereas particles with an integer spin are bosons. So in particular, if you have particles which have a spin of like 1/2, like electrons or protons, or three halves or 5 halves, those are fermions, and they can't occupy the same state as each other. But particles which have 0 spin, 1 spin, 2 spin, and so on, these are bosons, and they're allowed to be in the same state as each other, and in fact are sort of preferred to be in the same state. And so here are some examples of fermions. Electrons, protons, quarks. These are helium-3 nuclei. It turns out these are all 1/2 spin, whereas delta particle, for example, is a 3/2 spin. It turns out that the spin is actually a very big part of the identity of a particle and determines how it behaves and stuff. So the delta particle and proton are sort of fundamentally made of same particles, but because their spins are different, they behave differently. There's also some bosons listed below. So photons are the ones you're pretty familiar with. Helium-4 nuclei, of course, you might remember from thermodynamics, we may have talked about, I think I missed this, but we may have talked about superfluid helium, and this is fundamentally because it's a boson that you can do that pretty easily. Pions are also, they're a type of composite particle. They have spin 0. The W and Z bosons have spin 1. The graviton, which should exist if you have a quantum theory of gravity, would have spin 2 probably. And also the Higgs boson has spin 0. But I think that should be obvious given the name, that it's a boson. And I don't have a very intuitive explanation for this spin statistics theorem. It's kind of complicated, and like, frankly, I don't really understand it. But the idea that like we have been able to link to get together the like particle statistics and the like sort of spin nature of the particles is sort of a very fundamental result. Okay, and next.
Oh, okay. So now I'm going to talk about some kind of take aside from what Nicholas has been talking about, and now talk about some kind of applications of quantum mechanics and applying it to kind of these different fields. So first of all, we talk about quantum electrodynamics, which is kind of the first well-developed and kind of people say it's a very successful quantum theory, where we essentially just provide a quantum description of the electromagnetic force. And here pictured, you have Richard Feynman, who's a famous physicist who worked on QED a lot. And he kind of described it as the jewel of physics, because it's been able to kind of give us really precise and really give us a strong predictive theory in physics. And okay, Nicholas, you wrote this number. What is this?
Yes. So this is the G factor of the electron. I've just put it here because of how many digits that we know it to. Like when we say that like QED is sort of the most successful theory, most precise predictive theory we ever have had in physics ever, like that's not an understatement. So when you start with classical mechanics, so the G factor, just as a detail, is like how the spin of a particle is related to let's see, how is the spin of a particle related to something? Hold on, I'm blanking a little bit. Let me look this up. I'm sorry.
Regardless of what it is.
It's how the spin of a particle is related to its magnetic moments. There we go. And it turns out that if you just sort of model the electron as like a hard, negatively charged sphere, like that's like completely uniform, then you get some number. But it turns out that in reality, it's the number is like G times bigger, so it's like 2 times bigger than that. If you go to the Dirac equation, it turns out you can predict this number is 2, but you predict it to be exactly 2. But in quantum field theory, in quantum electrodynamics, it turns out you can do a whole bunch of calculations and find out that it's this number. And then you can go into a particle accelerator and you can check that it is in fact this number. And this, I don't know if I haven't counted these number of digits exactly, but on Wikipedia, it says that there are like 12 or 13 digits here. So you basically predicted this number to 12 or 13 digits. Which is extremely
crazy.
precise.
Yeah,
that's like insane. You like never do that basically.
Yeah. Yeah, so QED is pretty successful and it's very well established as well. And so Richard Feynman kind of described it kind of using these 3 basic principles, which is like to summing up QED, which is like a photon goes from one place in time to another place in time. An electron goes from one place in time to another place in time. An electron then emits or absorbs a photon at a certain place or time. And so this kind of sums up what QED is. Obviously, there's more complicated things behind it, but one way that we've been able to kind of very intuitively kind of represent these processes or these interactions are using something called Feynman diagrams. And so these are pictorial representations of the interactions that happen in QED. So to kind of describe what this is, it kind of looks crazy. It's just like a bunch of lines and stuff, but once you kind of learn what the different parts are, it's actually pretty fun to kind of decipher what is going on here. So here you can see there's a bottom axis which represents time. So that's just saying that as you go from left to right, this is kind of representing what's happening in time. And so you see that we have these straight lines of arrows, and so arrows pointing towards, like pointing forward in time, are electrons, while arrows pointing backwards in times are positrons, which are the antimatter equivalent to electrons. So here we have an electron, and then like a positron and a positron. And here in the middle, the squiggly line represents a photon. Also, you can see the gamma, which is the kind of the Greek letter for photons. And so we have kind of these different parts. And there's also one more rule in QED, which is that every vertice, which you can see here, kind of connects a forward straight line, a backward straight line, and a photon. So those are kind of the fundamental rules of like building Feynman diagrams in QED. So if you follow those rules as well as conserve momentum, in the sense that like you don't have one particle going in and like 4 particles going out. As long as you conserve momentum and follow these rules, you can essentially create or kind of represent pictorially an interaction that could theoretically happen in QED. So just as a quick kind of fun review, I wanted to see if maybe somebody could, or you guys could kind of try interpreting a Feynman diagram. So here, instead of, I mean, whether the time axis is like the X or Y axis is kind of, they're both like conventionally used. So here in this case, time is going up. Does anybody want to kind of just shout out what they think this is representing or kind of describe what's going on here? So as a reminder, we have an electron here and a positron here coming in, and then you have photons. So does anybody want to try their hand at explaining what's going on? If not, that's okay. So what's going on here is basically you have a proton. What I like to do is, like, as time goes up, I just like to kind of like use my fingers to kind of say, okay, so a proton, or not proton, sorry, an electron and a positron are going in, and essentially they're coming in and annihilating with each other. And what that does is, when you have antimatter matter annihilating, you have a release of energy, and that's in the form of photons. So what you see here is an electron positron annihilation, and that produces energy. And to conserve momentum, we have 2 photons coming out.
And yeah, notice how, yeah, so I think it's a very good point to just sort of notice that, like, even though this diagram is a little more complicated, it's still fundamentally built out of like these rules of like, you have one like electron line going in, one going out, and like a squiggly line coming out. Like, this is constructed out of 2 of those.
Yeah, and also just a sidebar, it's, as you can, if you kind of think of it in the time axis, it's happening instantaneous in time. So that just kind of represents an interaction. Yeah. So, I mean, these are just some more examples of Feynman diagrams in QED, and they might seem confusing, but if you kind of, you can try practicing yourself. If you're just kind of going through it, it's actually not that bad. Like, for example, this one, you can see, okay, you have an electron and a photon coming in, they interact, and you can think of it as a photon is being absorbed, and then the photon is then being emitted out again. Or if you kind of like look at this like example C, I think this one's pretty fun. You have an electron and a photon coming in, and then the photon will spontaneously become both an electron and a positron. And then that positron will then annihilate with the original electron, producing a photon. And so if you actually look at it, you can see that the end results and the beginning results are actually the same. You have a photon and electron going in, and you have a photon and an electron going out. So there's kind of like the conserved momentum.
Yeah, I guess, can we go back a slide?
Yeah.
So I wonder if people can sort of think about what happens if instead of time going like increasing upwards, it goes up to the left, sorry, to the right.
Oh, like switching to time and space?
Yeah.
Okay, yeah.
Like what is, well, how would I interpret the diagram in that case? Anyone have any ideas?
Yeah, so this would be time, and then this would be space. So just kind of, yeah, think of the narrative.
Yes, you are absolutely right, Jack. Yes, Alexander, that's right too. I think like scattering is the word that you would use for that event. Yeah.
Yeah, that's, if you actually see, this is actually the same thing as this, just flipped. And this would be, yeah, an electron, not a positron. So it's actually pretty cool, and like it's pretty succinct, and it's like a really cool, intuitive way to understand these. On the other hand, like kind of complicated, like mathematically complicated situations.
Yeah, and I want to say another thing, which is that when you actually do a calculation like this, like sort of the way you're supposed to think about it is that you only know what goes in and what comes out. You actually don't know what happens in the middle, so you actually have to go ahead and add up every single possible diagram.
Yeah.
And then like they might interfere with each other, for example. They don't just straight add up.
Yeah, exactly. So kind of as Nicholas just mentioned, when we see these Feynman diagrams, in reality, when we're like actually in the lab, the only things we actually know for sure is happening is what's going in and what's going out. So kind of what's happening in the middle, it's kind of like a question mark. And so in reality, you could have these things called virtual particles, where they're not really physical in the sense that like we see and measure them to be there like in the process, but they still represent possible kind of interactions or possible pathways that this kind of interaction could go through. And so when you're considering these Feynman diagrams, you can actually have like an infinite possible like kind of in between middle layer, and you have to add them all up, and kind of just like kind of like in the path integral formulation that we talked about in discussion, where you kind of have these infinite paths and then you add them up. Here as well, these kind of infinite paths can also be added up and then interfere with each other. And so we can kind of see this in kind of an analogy, or not analogy, but like kind of like an added point to this is something called the fine structure constant. So this is a dimensionless constant that essentially determines the strength of the electromagnetic force. And in QED, we say that every vertex in a Feynman diagram, you multiply, like every vertex you have multiplies the likelihood that the interaction occurs by this fine structure constant squared, alpha squared. Alpha, we've like measured it, and it's approximately, or I mean, we're still trying to fine tune it, but approximately we say it's a value of around 1/137. So when we say that every vertex multiplies the likelihood by alpha squared, we're actually, because alpha is less than 1, we're saying that the more vertices you have, that decreases the likelihood of that interaction happening, or vice versa. If you have less vertices, that means it's a higher likelihood. So kind of going back to here, even though you have like all these infinite possibilities, if you can like technically create some kind of like simple scattering Feynman diagram of like some crazy virtual particle, some crazy kind of thing in the middle, but the reality of that actually happening is pretty low because of this kind of probability rule with the vertices and the fine structure constant. So yeah, moving forward. So before we move on, I wanted to kind of do an overview of the fundamental forces, because this is pretty important in particle physics. So there are 4 known fundamental forces of the universe: the strong force, the electromagnetic force, the weak force, and gravitational force. And we're all pretty familiar with the, like, electromagnetic and gravitational force, but you might not have known about the strong and weak force. And so the strong force broadly is a force which holds the nucleus together. It's the force that keeps the kind of positive protons together, and even though they like want to repel because of the electromagnetic force. And then we have the weak force, which kind of facilitate neutrino interactions and kind of induces certain particle decays. The thing I want to kind of emphasize here in this kind of graph is looking at the strength and ranges of these 4 fundamental forces. So in reality, you know, we kind of think of, or at least for me, before, I kind of intuitively thought of gravity as this like super strong force. It like holds like planets together. It's like incredibly strong. But in reality, if you compare it to the other 4 forces, it's actually the weakest force. And the strong force is considered, I guess it's the strongest with the strength 1. While electromagnetic, like I mentioned before, its strength is determined by the fine structure constant, so 1/137. So you have like these broadly very differing strengths, as well as ranges. So something like the electromagnetic and gravitational force, we consider the range to be infinite, but we don't necessarily, but we do know that as a function of distance squared, as an inverse square law, the strength of these 2 forces decrease. So even though technically it is infinite, I guess at some point we acknowledge that, like, okay, it's just like so negligibly weak at some point, like at infinite distance, that we just kind of call it 0. But in reality, it is kind of considered infinite, while something like the strong and weak force actually have a very distinct range. And we're going to kind of delve into that with the strong force.
Yeah, I will want to give some intuitive color to what is meant by the like gravity is so weak. Like how is that possible? Well, just from an intuitive perspective, you have weight because the entire like gravitational field, like gravity of the Earth, is pulling down on you, but you're not falling into the ground because the electromagnetic forces of just the electrons like in your body, like, and the electrons in the floor are like, that's like totally enough to stop the entire gravitational field of the Earth. That's sort of like the comparison.
Yeah, one thing that kind of confuses people is like, oh wait, what? There's only 4 forces. How do you like? How about just like pushing somebody? Which one of that? Like, what is that considered to be? And that's all basically kind of all the day-to-day interactions we kind of consider as forces are kind of categorized under electromagnetic force. And that's precisely what Nicholas was saying, in that the force we experience kind of just like, the reason why I'm not falling into like this couch right now is because my electrons, my atoms are being electromagnetically repelled by the like electrons of this couch. So if you kind of think of it in that context, you're like, wow, they're tiny particles, but they're pretty damn strong. So yeah, moving on. So we had QED before, and so now, if you could kind of guess, we're going to talk about a quantum description of the strong force, and that is called the quantum chromodynamics. And so QED was developed in like the 20s to the 60s, like 1920s to 1960s. And as QED was really kind of taking full force, there were three physicists who kind of took quantum mechanics and kind of the context of QED and then applied it to the strong force to develop quantum chromodynamics. So there is a lot of analogies between QED and QCD. So first of all, I guess like the biggest question is, okay, why is it called chromodynamics? And that's because physicists are really creative and they decided, okay, we need to think of different charges, and we already have plus minus taken from electrodynamics, so we're going to say color. So yes, we say like red, green, and blue, as well as their anti-versions, are the types of charges that QCD deals with. And so unlike QED, which had only two charges, well, in actuality, as Nicholas mentioned, you can kind of think of one charge versus the other being the anti-version. So just like how the positron is positive and the electron is negative, that was kind of like the analogy. In QCD, we have three charges, and each of those charges then have their own anti-version. So there's kind of like 6 charges in total. And we also have gluons. So gluons are the force carrier particles that mediate the strong force for particles that have this color charge. And so kind of the analogy in QED is we have charged particles, and the kind of force carrier particle that mediates the electromagnetic force are photons. But however, in QED, we know the photons are completely neutral. So in a way, they don't necessarily interact with each other under the electromagnetic force. We do know that gluons, though, have their own color charge. So that kind of complicates things. So the particles that have this color charge are called quarks, and they're kind of the building blocks of other particles, which we'll go into later, but just know they're called quarks. And so the point I'm trying to kind of make here is QCD is, if you could kind of tell, is a lot more complicated than QED, in that QED was very like succinct and beautiful, and you just had like 2 charges. It was really nice. The mediating particle didn't interact, so it was like really nice. But QCD kind of doesn't have that, and that if you look at the classical theory for QCD, which is called Yang-Mills theory, it's not linear. So basically what that means is the math itself for QCD is really complicated. We can't use like really nice mathematical tricks. It's complicated. And also, unlike in QED, where we said like Feynman diagrams with kind of complicated, like lots of vertices, they don't really happen, so we don't really have to worry about them. In QCD, that's not the case, because the fine structure constant equivalent, which is a strong coupling constant, G, if you remember in the pictograph, it was like the strength was equal to 1, and so G is equal to 1. So the likelihood of, if you do the same math with QCD, you don't get any decrease in likelihood for kind of interactions of lots of diagrams. So that just means there's a lot more scenarios we have to deal with. So that just makes it a lot more complicated.
And I want to say one thing. So
yeah,
like things like the fine structure constant and like the coupling constant, we call them constants, but they're not really constants. They actually change if you go to higher energies. And so it turns out that if you go to higher energies, actually this constant G actually goes down. And so you actually can start using what's called perturbation theory. But like at like sort of normal energy scales, like everyday energy scales, it's pretty big, so you can't.
So another complication that I want to talk about are the gluons themselves. So just as like an understanding, like we had in QED, we had the photons, and photons, and there's only one photon, but to kind of mathematically allow for all different possible interactions between the 3 types of quarks, which are like the 3 quarks with like those color charges, there actually has to be 8 types of gluons, each with their own combination of these color charges. And like I said before, gluons themselves have charges, so they can directly interact with each other. So kind of in Feynman diagrams, we represent gluons as these kind of like spring-like lines. So here you can see they kind of they can interact with each other and kind of create those vertices. So they look kind of funny, but yeah, so it's just a lot of complications of QCD. So unlike QED, we don't necessarily, or physicists don't really say QCD is kind of this, has the same like completeness or like beauty to it, but it still does have a lot of predictive power. One of the biggest kind of accomplishments of QCD was kind of explaining these gluon interactions. So unlike in QED, where the electromagnetic force has that infinite reach, albeit like with a kind of decreasing strength, the gluon, the strong force interaction actually stays pretty constant. And you can kind of think of it in this animation. You have like two quarks combined or like binded together by the strong force, which is like pictorially represented by like kind of like that band or a tube. And so as you're kind of stretching, as you're applying energy to the quarks to kind of pull them apart, the bands is still maintained. And so we can say that it's still the force is still constant. It still exists there between the two quarks. So we don't say that as the distance increases, the strength of the force decreases. However, there is, what happens though is as you apply more and more energy and stretch out the two quarks, it reaches a certain point where you've actually inputted enough energy where it becomes energetically favorable to actually just create a quark-anti-quark pair of its own. And then so you'll create, as you can see in the animation, you'll create another kind of quark pair. And so what that means is then you can kind of think of it as resetting the strong force distance. And so you stretch it like far enough, but instead of like pulling apart quarks, you just get like another quark pair because you've just inputted that much energy. And so this has a lot of cool consequences. And so the first one is obviously this kind of embodies why the strong force has such a like a short distance or a short reach, is because that's kind of the point at which it just becomes more energetically favorable to just like create another quark pair such that you just kind of reset the distance. And so that distance is approximately 10 to the negative 15 meters, which is less than the diameter of a nucleus. And so it just kind of succinctly describes why protons are kind of kept together. Protons are, I guess I never explicitly said this, but protons are like they're made up of quarks. So they kind of fall under QCD, and so are neutrons. So this kind of explains why we are able to keep the kind of nucleus stable as it is, even though we have like two positively charged particles there, and you'd have like a repulsion force from E&M. We have the strong force, and it's close enough such that the strong force works. So, and this also explains why we don't experience a strong force in everyday life. On the other hand, in our scale of reality, we don't deal with the strong force because it just doesn't exist beyond 10 to the negative 15 meters. Another really big result of this phenomenon is something called color confinement. And as you probably might have kind of understood, is that quarks are then never observed by themselves. And what I guess kind of mean by that is you never really see them by themselves beyond this distance of 10 to the negative 15 meters. And they're always seen in nature grouped together in particles called, is it hadrons or hadrons?
I think it's hadrons.
Okay, it's hadrons. I never knew how it was pronounced, but let's just say hadrons. So quarks are always kind of bunched together in like groups of more than one, basically. And so kind of the more common kind of groups of hadrons are these mesons, which are quark-anti-quark pairs, and also baryons, which are three quarks of each kind of color, or not even each color, just three quarks, but not like anti-quarks, just three quarks. And this is kind of the group in which protons and neutrons fall under.
Right. So for both of these, you need the color to like cancel out, right? So if you have the three quarks, then they have to be like the three different colors, and if you have the meson, they have to be opposite.
Yeah. So it'd be like red, anti-red.
And I do want to say that sort of color confinement is a thing that happens, but actually people have never like exactly mathematically proven that, and that's like a big like problem right now.
Yeah,
But-
so it's kind of one of the reasons why like people have brought color confinement as a reason why we've never experimentally observed a quark by itself. In fact, when you look at the LHC and kind of the experiments they do, and they kind of smash particles together and they kind of observe the kind of debris, they're all hadrons. They're never individual quarks by themselves. And so this is kind of an explanation as to why. But like Nicholas said, it's not like a fully formed theory. And this is maybe one of the reasons why QCD is not as fully developed. And there's still lots of research being done on QCD. So while QED is kind of stagnant, I guess, in terms of research, QCD is still a very like active field, and people are still trying to figure out what exactly is going on.
Yeah, and one thing I want to say is that like usually you think like, oh, I have a model, like that means I can get the predictions, but it turns out in a theory like QED, but QCD specifically is like your predictions themselves are very hard to obtain because they might require a lot of computation.
Yeah, and this kind of goes back to what I was mentioning about how like complicated QCD is. There's just so many more factors you have to deal with. So a lot of people in like current day research are kind of pouring in a lot of like computational power into QCD to just kind of overcome just that huge like mathematical barrier. Yeah.
Okay, so I just wanted to sort of go over the standard canon of particles that exist, the standard model of particle physics, which is basically like the most complete theory of physics that we have. It's basically the framework of like what things exist and how they interact with each other. So I wanted to go over what kind of particles do exist, which are quarks, leptons, gauge bosons, and the Higgs. These are the particles that we know of that are like that we don't know what they're made of. Maybe they're actually fundamental, who knows? And there's sort of a little bit of a small, tiny periodic table looking thing on the right, which sort of details what the particles are. So you can see the quarks are in the top left, the leptons are in the bottom left. Then the like red column is the gauge bosons, and the Higgs is all the way on the right. So if we go to the next slide. Quarks, as Jana was just mentioning before, are basically these very tiny particles which make up the protons and the neutrons. One thing that's and you know basically interact with the strong force and stuff. And so one thing that's kind of interesting to note is that a lot, like if I remember correctly, most of the energy, most of the mass of a proton and neutron is actually not in the quarks, it's actually in their interaction. In the sense that if you added up the energy of the quarks that make up a particle, they're like much smaller than the particle itself. And yeah, so if you just sort of look over here, there are 6 different kinds of quarks, and they're divided into 3 generations. So 3 pairs of 2. So the up and down quarks, which are like the lightest ones, are 2.2 MeV and 4.7 MeV. So like that's just some a quantity of energy. Which is also mass because it equals mc squared. And you can notice that the proton is much bigger. It's more like 1 GeV. The neutron is similar. So a GeV is 1,000 MeV. So you can imagine like, how do I possibly like add together 2.2 plus 2.2 plus 4.7 to get 1,000 because of the interaction energy. But you also get sort of heavier, more exotic kinds of quarks called strange and charm quarks, which are at 96 MeV and 1.28 GeV. So you can notice that that's like a very large difference, but indeed, like these are not typos, like these are actually what the masses are, and they're extremely different from each other. These particles are heavier, and so they actually decay like down to the up and down quarks. There are some interesting theories that say like strange quarks can like comprise matter called strange matter, which like takes over everything. And I can't definitively say that that's not a thing, so be warned. And then there's the even heavier topmost generation of quarks called the bottom and top quarks. The bottom quark is 4.18 GeV, whereas the top quark is actually 173 GeV. So it's like way, way bigger than everything else, and it's pretty hard to study because of that. Like, so actually like the heavier a particle is, generally the shorter its lifetime is. And so it like decays like really fast. And so, as I said before, quarks, as Jana said, quarks can comprise mesons, which are like particle anti-quark pairs, which tend to like die pretty fast because like, you know, you have matter next to antimatter, but you might also have like protons and neutrons, which are what are called baryons, which are shown on the right. So a proton is 2 up quarks and a down, and a neutron is 2 down quarks and an up. And at low energy, and low energies, as we said before, they can only be found in their color neutral combinations. Next slide.
I just wanted to comment that these names are real, and that as like people have been finding these different like flavors, they just come up with more weird names.
Yeah, I'm kind of upset because I like people would sometimes call bottom and top quarks truth and beauty quarks, but
Yeah.
then some person was like, nah, like we gotta be serious. Let's call them bottom and top, and that's like the stupidest thing I've ever heard.
I know beauty and truth sounds way cooler, but what can you say? Okay, next slide.
Yep. And so, so here are just some examples. One fun fact is that free neutrons are unstable. So if you just have neutrons like floating in space, like not attached to anything, they actually decay in like 10 minutes or something like that. And it actually turns out that in the early universe, this was really important because like the neutrons that are around had a period of time where they would just decay. But I think we talked about this in cosmology. And up and down quarks can decay into each other, and heavier quarks usually decay like downwards really fast. And so that's basically how quarks work. Next slide. The other kind of particle, the other kind of fermionic particle in the standard model is called a lepton, and there are 6 leptons. So they're divided sort of, you can sort of think of them split into 2 generations, like this sort of this chart on the right. 3 generations, 2 pairs, one column is just the standard leptons, the other ones are neutrinos. So electrons are like half an MeV, muons are 106 MeV, so like what, 2,000 times big, 200 times bigger, and tau particles are like 1.7 GeV, so like I don't know, 20 times bigger or something like this. Each of these has an associated neutrino, which in standard model math, I believe they're considered massless, but they're not actually massless. As it turns out, people have shown that they're not. And so that's sort of a shortcoming of standard model. And so weak interactions, weak force generally involves like leptons and quarks. So for example, neutrons, as I said, might decay into protons, as well as an electron, as well as an electron antineutrino, for example, is the reaction below. Next slide. And neutrinos are a very interesting thing because they're extremely hard to detect, and they were first inferred when beta decay existed. We figured out what beta decay was, and we're like, wait a second, spin doesn't seem to be conserved here. There must be another particle which is very light, which we're not detecting, which is moving away. And so these are produced in large numbers by the sun and also astrophysical events at many energy scales. And the solar neutrinos, it would take, if you had a solar neutrino that was just moving, it would take about like a few light years of lead to get it to stop. That's how little they interact with things. They interact gravitationally probably because they have mass, but they don't interact electromagnetically or strongly. There's also thought to be a large background of low energy cosmic neutrinos that we'll probably never measure because of how low energy they are. It turns out that neutrinos actually oscillate. So they have 3 flavors: electron, muon, and tau flavors. And it turns out that they actually oscillate between each other. And the fact that they do means that they have a mass. Yeah. So next.
Also, just a fun fact. If you like put out your thumb like this, and like at any second, there's like billions of neutrinos just going through your thumb. But I mean, they just are so weakly interacting that we don't, I mean, obviously we don't ever experience them, but you can imagine how frustrating that is for physicists because there's so many neutrinos out there, but they're so hard to detect. And if you were able to detect them, they would really, have a lot of answers in terms of like cosmology, particle physics, but they're just so incredibly hard to detect. And if you look at the detectors meant for neutrino detectors, they're pretty elaborate, and like oftentimes they're like built like miles underground, and they're like in mines, and they're like these huge vats of like really pure like argon, liquid argon or something. It's pretty impressive, but yeah, they're hard to detect.
Yeah, and one other fact which is sort of going the other way is in a supernova, it turns out that people believe most of the energy actually goes out through the neutrinos, and the neutrinos actually have a big role in like driving pressure. So even though they interact so little because there's so many of them, that like they actually like, can push out like, you know, have a big role in sort of pushing the star out. And there's actually an interesting XKCD article where he basically figures out like that you could actually overdose on neutrinos if you were like near a supernova. I mean, you die from other stuff first probably, but like the fact that you can do that also talks to how like insanely energetic supernovae are. Yeah.
Cool stuff.
Yeah. So there are also the gauge bosons, which are the force carrying bosons. And so gauge, as in they have a similar gauge symmetry structure to E&M that we talked about before. Bosons, which carry the fundamental forces, are the following: the photon, which is electromagnetism, the gluon, which is the strong, and the W plus and minus and Z bosons, which are the weak force. You might notice that I'm missing gravity, which is because we don't have a quantum theory of gravity. And we've never like measured a graviton or anything like that. And so we mentioned before that the weak force bosons are weird because unlike the photon and gluon, they actually have mass, and so they decay. And this means because they decay, like this force basically has the shortest range of all of the four forces, because like if two particles are too far apart, then the force carrier can't move between them without decaying, basically. And so it turns out that we have confirmed that there's something called the electroweak force, which is if you increase the energy scale high enough, E&M and the weak force actually merge together into the electroweak force, because we're very creative like that. And that's super cool. At some high energies, these forces are actually the same, and only at low energies do they sort of split off.
Just to add another thing, that also kind of suggests that if you go back in, like, if you think of the timeline of the universe, and if you go far back enough, then, you know, physicists predict that there is like one unified force where, like, I mean, at some high enough energy, all of the four forces were combined. And there's a lot of kind of theoretical physics being done about that, but obviously we have not reached that stage yet, but pretty cool. Okay, so we're gonna just kind of wrap things up here with the last kind of part of the Standard Model, which is a Higgs boson. And probably you guys maybe remember when 2012 it was kind of discovered, and it was announced that it had been like experimentally seen in the LHC, and it kind of, there were waves of like popular media talking about it, and some people called it the God particle, and there was a lot of media coverage of it, but in fact it was kind of something kind of known in the phys community since the 60s. That's when it was kind of first predicted. And it's generally known to kind of be the particle that creates mass, but it's a bit more subtle than this. And so the Higgs boson itself as a particle is not what creates the mass, and what it is it's an excitation of the Higgs field. So just as Nicholas talked about like certain fields and how excitations and like wiggles in those fields kind of represent particles as we know it, the Higgs boson is kind of the analogy of that to the Higgs field. And so kind of the prediction or theory that we have for the Higgs boson is shortly after the Big Bang, and as the universe began to cool, the Higgs field kind of was frozen in place as the energy kind of decreased. And what happened then was any particle that then interacted with the Higgs field, that interaction is what kind of gives that particle mass. And so the more you interact with the Higgs field, the more mass you have. And obviously there are particles that don't interact with the Higgs field, such as photons, and so hence why they don't have any mass. So to kind of explain a bit further than kind of that general overview, so in quantum mechanics, and as you kind of talked before here, harmonic oscillators are really important, and we can kind of see in 3D that we can kind of pictorially represent this as something which is kind of unfortunately called the Mexican hat potential, or maybe you can kind of see where that name comes from. It kind of looks like a hat. And so what you can kind of see here is at the top, where you kind of have this ball, we have an unstable equilibrium. And just as a reminder of what that means is it's an equilibrium in which when you perturb it slightly, it kind of falls away from the equilibrium point. So as you can imagine, if you had a ball bouncing at that top of the hill right here, the ball would then fall. And so this is actually the kind of the act of that ball falling is what we call spontaneous symmetry breaking. And this is important in how we say particles gain mass. So once fallen, so the ball that I've been describing is actually representative of a field, of the field. And so this field can either vibrate radially, which is kind of like up and down, kind of like around the classical harmonic oscillator shape, or it can kind of vibrate radially. And so these oscillations themselves, like I mentioned before, are kind of the force mediating particles. And so this kind of first case of it vibrating radially up and down is the Higgs boson, while the second case of it going circularly is something called the Nambu-Goldstone boson, which is actually non-existent. It doesn't physically exist. It's more of an artifact of gauge symmetry, which is just complicated math, but just know that it exists, or technically doesn't exist. And so what's happening here is we say the Higgs is said to oscillate at some non-zero value, and which is called the vacuum expectation value. And so just think of it as the Higgs is oscillating, kind of that, when we kind of describe harmonic oscillators, we kind of set it at zero, but we know that for the Higgs, we can say that it's at some non-zero value, so that when it's kind of interacting in a second field, so whether that's like for an electron, for example, like an electron field, when they're kind of overlapped with each other, or that's how I like to think of it, when they're overlapped with each other. In this kind of the second field's point of view, and the electron field's point of view, the kind of that non-zero value, the VeV, is then kind of interpreted as this like added energy or added mass. And so VeV is not like a constant value, it differs, and hence why for different fields you get different masses. That's kind of, there are
so the Higgs at some point has like a vacuum expectation value, but it turns out that because it's like, what spontaneous symmetry breaking is in this context is like, you can imagine if you took a pencil and like stood it up, it would fall down, but it would sort of, the direction it falls down is kind of random. And so it turns out that at a certain point, like the Higgs will take some vacuum expectation value, the Higgs field will, but at some other point in at some other place in the universe, it might fall some different way. And then there might be a mismatch and stuff like that. Yeah. And so like the interactions that a particle might have with the Higgs field, sort of like the strength of that interaction will determine, and the value of the VeV will determine like what the actual the mass will be.
Mm-hmm. Yeah, this is kind of an attempt at giving a kind of intuitive explanation, somewhat of an intuitive explanation for kind of the mathematics behind it. But there are some pretty good videos on YouTube where people kind of, like a very common explanation for the Higgs field is kind of this concept of like a crowded room. And like, if you have a popular person, and like, if you're in a party and you kind of have somebody who's like the host of the party, so there's a lot of people kind of interacting with that people, kind of the general crowd will kind of like clump around that person, and you can kind of interpret that as like an interaction with the Higgs field, which is like kind of the crowd, and like how they kind of attract more of the field towards that one person per se, and that is what we kind of interpret and describe as mass. So there are some cool videos out there that kind of describe in that sense, which might be a more intuitive explanation for how the Higgs field work. We're almost out of time, so
yeah, so this is the last slide. I just want to sort of emphasize something that you guys may have heard about before, but the ultimate ambition is to basically unify the theories together. So over here we have a plot of the strength of the field versus the energy. And so we know that if you increase your if you increase the energy you're probing your system at by like a certain amount, you end up merging together the electromagnetic and weak forces together into the electroweak force. We know this to be true as a fact, as an experimental fact. But then we believe also that if you increase the energy even more, eventually you'll get to what's called a grand unified theory, or a GUT, which is when you merge the strong and electroweak forces together. We don't have one of these yet, or we definitely haven't confirmed how these forces blend together, but we believe that that possibly at some larger energy scale, there's something called a TOE, which is where the strong electroweak and gravitational forces all come together. This stands for the theory of everything. I didn't make these names up. I'm sorry, but like you can see how like as you increase the energy scale, the like coupling sort of blend together, and then you sort of get one big fundamental force at large energy. So this is the ultimate ambition. When you hear about people talk about like string theory or loop quantum gravity, like those like theories are not necessarily only to produce a grand unified theory, but like one of their big ambitions is to do that. And so that's like one overarching theme of the field, is that people want to like figure out what exactly this is. And it's seeming to be very hard, because how do you actually probe a system at these energies is, you can't basically. So that's a summary of particle physics. We've sort of gone through like how, like many top subjects, which include like how do you merge together quantum mechanics and special relativity, which we have done. I don't want to say seamlessly, but we did it.
Technically.
Yeah, and then we talked about the kinds of particles that exist, the kinds of quantum field theories that actually govern our universe, and like what kind of particles there are, and I hope that was a reasonably clear introduction to the field. I would say that none of us are particle physicists, so there's like so much more that we even don't know.
Yeah, but I hope like you didn't get too discouraged by like all the names. Definitely like just looking at all the like different flavors and all those mumbo jumbo words for the standard model can be kind of intimidating, but hopefully kind of got a gist or a general understanding of what the current known fundamental particles are. So
does anyone have any questions?
yeah, we're technically over time. So people are free to leave, but if you do have questions, feel free to ask.
You might want to turn off the recording.
Yes.